we can talk about probability of more complicated events. What happens to union of events? So let's say A and B are two events. You remember that these are subsets of the sample space. So then if someone asks you what is the probability of A union B, intuitively it is quite clear that it should be equal to PA plus PB if A and B are disjoint. This does not come as a surprise. So make sure that you intuitively understand it. But in a more general case, we can say that PA union B is probability of A plus probability of B. But this means that we have taken the probability of some events more than once. So we subtract. And as an exercise, prove this. Remember, we had this definition that probability of a set is just the probability of all the elements in the. So once we have the probability of an event, it should be easy to calculate probability of A. So this was a simple example, but now we might be interested in finding out probability of A union B union C. In this case, our first guess would be PA plus PB plus PC, which would be true if all these three events were disjoint. But you see that we are calculating or adding probabilities of events more than once, which were in both A and B. So if the sample point was in both A and B, then we are adding it twice. If a point was in all three A, B, and C, then we are adding it thrice. Shouldn't do that. So let's correct our estimate, subtract all these probabilities. But now you might want to check. So what happens if the element was exactly in A and B, but not in C? You would see that I would count it here, and then subtract here. So that is counted exactly once. That's okay. But what about if there was an event which was in all three, A, B, and C? Have we counted its probability correctly? It is counted in this, this, and then again subtracted thrice. So that means it was not counted. So then the correct thing would be this expression. And you can check that all cases are counted. This actually gives rise to a formula which you know as inclusion exclusion. The formula says that probability of union of some events, you take summation over all possible sets and calculate the probability of each of these intersections. If this notation is new, then pause for a moment and just make sure that for n equal to 3, this formula gives rise to this expression. So I'm just writing this formula more generally with a new notation. So it should be fine to you. It is just I'm calculating A1 union A2 union A. What is the use of this? Mostly we use this when we say that, let's say A1, A2, AN, these are the probability of some bad events. So A1 is a bad event, A2 is a bad event, AN is a bad event, and we want to find the probability that no bad event happens. So can you write this? No bad event happens. That's set mathematically in terms of A1, A2, AN. Take it as an exercise. It's not very hard. You realize that it is, if you take the union, which for which we actually wrote down the formula, and take the complement of it. Remember, A1, A2, AN, all these were bad events. So this tells us that no bad event. Then we are interested in this probability that no bad event happens. This is 1 minus probability A. And we know this expression. Actually, we can think of one as probability intersection I is element of phi A. This would be my claim. I would say that if I take the intersection over the empty set, then my probability should be 1. The idea is that as we take intersection of more and more elements, then the probability decreases. If I am taking intersection over empty set, that means there is no intersection, then the probability should be maximized. So this you can assume as a convention, or you can convince yourself that this is 1. This makes sense. Intersection of one elements decrease. So for least number of elements, the probability should be maximum, which we call it to be 1. So using this, we get the probability that no bad event happens. This is the quantity which we are interested in. This is summation over S. Now we can take summation over all possible subsets. I will just show you the expression. This was, so when I take 1 minus this thing goes out and we get intersection I element of S. So this is our formula for no bad event happening, where A1, A2, An are all the bad events. I will finish this lecture by looking at an example for this. And this is the case when you have n letters and n envelopes. All, both of them are numbered 1 to n, so there is only one correct envelope for one letter because of this numbering. And we are interested in the probability that no letter goes to the correct envelope. So we place the letters arbitrarily, randomly. So every permutation is equally likely. That is going to be our sample space. And the question is, what is the probability that no envelope goes to the correct letter? So the first thing is to define our bad events. So our bad events are the ones when actually the letter goes to the correct envelope. So that means AI should be the event that the ith letter goes to the correct envelope. So now to apply this formula, we need to figure out, and if you notice, this means that exactly, not exactly, but at least this many letters go to their correct positions. So that means these letters go to their correct positions, remaining ones I can permute them independently. And then the total number of permutations is n. I would like to tell you the meaning of this because this is a confusion for many students. When this happens, that events in S definitely happen. But for events which are not in S, we have no idea. That means this is not the probability that exactly events in AI are happening. This is the probability when events in S definitely happen, but outside S, we have no information. So given that, we figured out that in the case of letters and envelopes, this probability becomes this. And then applying the formula of inclusion and exclusion, we get that no envelope goes to correct position. So I'm just going to substitute this in my formula derived earlier, and I will get summation s minus 1 to the s and then n factorial. Now you realize that this quantity only depends on the size of s. So then this can be simplified to, and we have n choose k success of size k. So we get this formula for inclusion exclusion. It looks like 1 minus 1 by 2 factorial plus 1 by 3 factorial and so on. So if you do some bit of analysis, this approaches 1 by. So as n becomes close to infinity, the probability that no envelope goes to the correct envelope, no letter goes to the correct envelope, becomes 1 by. So we saw one way to model probability experiment using sample space and probability distribution function. And remember that this was the case when the sample space was discrete. It turns out that this is not the most general framework. In the next lecture, we will see that we need a more general probability to tackle more cases, especially when the sample space is discrete, and we will see it